This video is going to take a look at how we can conduct a hypothesis test for a proportion. With proportions, it's nice because we will always use the normal distribution as long as NP and NQ are both greater than or equal to 5. Remember, N is the sample size, P is the proportion of successes, and Q is the proportion of failures. As we calculate these values, P and Q come from the null hypothesis, not the sample, because we always assume the null hypothesis is true. The only difference between a hypothesis test for proportions and a hypothesis test for means is the z-value formula. The z is going to be p hat minus p over the square root of pq over n. P hat is the sample proportion, while p is the population proportion. The population proportion comes off of the null hypothesis. Notice the denominator are also both coming from the population proportion, because we always assume the null hypothesis is true. So let's take a look at an example. A certain eye surgery has been 30% effective. That's overall for the entire population. So that's going to be our P. A new procedure is developed and it's tested. Here's our sample, 225 patients, 88 were successful. So 88 were successful out of 225. That's our sample proportion, P hat. At the 1% level of significance, we want to know if this procedure was more successful. 1% is our alpha of 0.01. That's the lowest probability where we'll still believe the null hypothesis is true. So for our null hypothesis, since we're talking about a proportion, not a mean, we're going to say P equals, and the population proportion claims to start at 30% effective, 0.3. The alternative, what we're trying to prove, is that we're being more successful. We want that population to be bigger than 0.3. So if I were to draw my picture here, we want the right tail. If the mean is 0.3, we want to be bigger than 0.3. We want the right tail to be our rejection region. Let's calculate the P hat, the sample proportion. P hat, we had 88 successes out of 225 patients. When we do that 88 divided by 225, we're going to end up with, let's round it to 0.39. So now if we calculate our z, z is the sample proportion minus the population proportion, divided by the square root of the population proportion, the population failures, divided by n. So P hat, we just found out, was 0.39. Minus P, we claimed, is 0.3. Divided by the square root of P, 0.3, times Q. Q is the failures. If P is 0.3 or 30%, Q is going to be 1 minus 0.3 or 0.7. So Q is 0.7. Divided by the sample size, which was 225 patients. To help me with my calculator, I'm going to put that numerator into parentheses. And so I've got 0.39 minus 0.3 divided by the square root of 0.3 times 0.7 divided by 225. Being careful to keep that whole denominator in parentheses, I get 2.95. That z-value of 2.95 is what we're going to plug into the z-table to find our area in the tail. Let's go to Excel to do that. We're going to say equals norm.s.distribution, 2.95, and when we say true, we end up with 0.9984. 0.9984, but remember, Excel always gives us the area to the left. We want the area to the right in this case. So we'll subtract from 1 to get 0.0016. Our p-value is 0.0016. That's the probability our null hypothesis is true. And alpha, we said, was 0.01, which is the smallest probability where we'll still believe the null hypothesis is true. Because our p-value is smaller than our alpha, this means we will reject the null hypothesis. In other words, we claim that we have enough evidence to suggest that the proportion of successful procedures is greater than 0.3 or 30%, or we support the doctor's claim that the new procedure is more successful. Hopefully this video has been helpful for you as you look at conducting hypothesis tests with proportions. You'll find it's very similar to what we did with the means when the standard deviation was known. The only difference is we have a slightly different formula for how we calculate our z.